How are you, Professor?
I'm fine, thanks. How is everybody doing?
Pretty good.
Pretty good. Pretty good. I am working on your latest progress reports. I have not put them out there yet. I'm still setting them up. So I've updated the grades based on what's in the textbook and on Mimir. And I'm in the process of recreating the original progress reports so I can send them to you on Slack. I'm going to do that. If we have time during class, I will finish it. There's a few more I need to do, and then I need to put them out there on Slack so that you guys can see your final progress report for the semester. There's been a few updates. Just so you know, there was some errors that I had in the participation activities from the textbook. I went back and redid them all based on what the textbook has currently for your participation activities. So that should be pretty much complete. And I also updated homework number 6. There's been a few great changes since I sent the progress report out last Thursday. So I don't know if you guys have any questions for me, but that's where I'm at. Okay, and also your exam is all set to go. It is on Blackboard. It's all on Blackboard. It's multiple choice. It is set to go live on next Monday at midnight in the morning, and it will run Monday. I believe it was Monday that we had decided for this class, or did we decide on Saturday? I forgot what we decided.
Saturday. Saturday.
We decided that Monday was the time, or Saturday?
Saturday.
Saturday. So your exam is set to go live on Saturday at midnight in the morning and go through Monday at 11:59 p.m. Okay, all of that is in the announcements that I made on Slack and an email. Okay, having said all of those things, any questions you guys have for me? The exam does not have a Mimir component. It's all multiple choice. Questions? Can we go over hazing? Hashing. Yeah, what about it? What do we need to know about hashing? Henry, you please speak. This is a good time for you to speak. Okay, so why don't you go grab your mic and then come back. And then when you have that, then we can ask the question. Anybody else?
I saw that the final was gonna take like, you're allowing 4 hours for each attempt, right?
I forgot. What did I say in my email?
Oh, I read it somewhere. I don't remember if it was on Blackboard or your email.
I made an announcement on Blackboard and on what you may call it. Yeah, it's 4 hours to complete the exam.
Okay. How many questions are there?
Enough.
Oh, okay.
I have to go back and count, but it's enough questions.
Is it like a lot more than the midterm exam? Is that why?
The midterm exam also include the midterm exam. The multiple choice part was shorter because there was more. There was also a Mimir component.
Okay.
This
Yeah.
one has no Mimir component, and it's therefore longer. That's why it's 4 hours.
Okay. All right. Thank you.
Okay, and 4 hours is kind of generous in my opinion. I think you could do it in 3 hours, but I figured I'll leave it at 4 hours so that you guys can feel relaxed as far as time. I don't believe in pressuring people on time for exams. I think people should not feel pressure. You could feel all kinds of pressure about an exam, but time should not be one of them. Anybody else?
All right. So my question about hashing is because I have like some trouble like understanding like the modulo operator when it comes to like arrays. So like circular indexing is kind of like iffy part for me too. But in terms of hashing, I think if I just saw like examples of like squaring two, like the square hash, just different examples of how you can hash into buckets, I think that'll probably help me. Just understanding like the modulo operator and how it like really works in arrays.
I hear two different questions in there. I hear a question not understanding the modulo operator. That's one question. And I hear another question about the kind of hashing strategies to deal with collision. Which one of those two or both?
I just want to be able to understand more how the modulo operator works with the arrays itself. It's not the modulo operator, it's more the concept of putting of just like indexing and making sure you don't collide with
Okay.
previous like inserted items.
All right. So let me bring up my pad over here so I can write down. Okay. And I'll share my screen and then we could talk a little bit about that. Okay. Give me 1 second to bring this up. It takes me a second to get this started. Okay, so I'm going to share my screen and then we'll talk about it. Let's do that. Okay, can you see my writing pad?
Yeah.
Okay, so when we're dealing with arrays, right? Arrays are discrete, right? There's an array and it has so many spots in it. 0, 1, 2, 3, 4, 5, 6, 7, 8. So this array has length 9. Okay, correct? All right, so now I have an object, I don't know, person. Person is a class, and every class in Java has some methods defined for it already that you inherit from the type object. Okay, things like toString, things like equals. Okay, if your class overrides those, you can override them to create them to do something. Okay, like toString, you can make it print whatever you want it to print. Equals, you can say, okay, I can compare two people to each other. There's also a method called hash code. Every class has a hash code. It can either be provided by the object class or you can override it in your own class. Hash code produces an integer. Okay, it returns to you an integer. Some kind of a strategy to come up with a hash code for this particular object. So when you want to hash something, if these are my buckets, I have a set of buckets of 9 buckets. There's no guarantee that this int that's going to come out of the hash code is going to be in the range 0, okay? Hash code less than or equal to 8. We want to guarantee that that hash code is in this range for us. And the way we do that is we take the hash code and then we modulo it by 9. Okay? Modulo operator returns to you the remainder. If I divide any number by 9, I'm going to get a remainder between 0 and 8. There's never going to be a remainder of 9 because I'm dividing by 9. So if I'm dividing by 9, the remainder is going to be in the range from 0 to 8. And that's how I obtain the bucket. Okay? The bucket is obtained by taking the hash code and moduloing it by the number of buckets that I have. And that gives me the index of a specific bucket. We're okay so far, Henry?
Yeah.
So far you understand how the modulo operator relates to the hash code?
Yeah. This made it clear. Just for like a slightly better understanding, can you go over the not checked yet versus like
I'm
when
going to come to that. This is
All right.
not, this is just in order to find what bucket this needs to go into. All of this
All right.
is to find out the number of the buckets. Okay? So the number of the bucket is coming out from taking the hash code, modulating it by 9, which is the size of my hash table, and that tells me the bucket number. Okay? Now, how do I deal with collisions is the question. Okay? So we described multiple types of hash tables. Okay? Multiple ways of dealing with collisions. The first way of dealing with collisions is the one that we did our homework. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. That's my hash table. I hash an object in our table, in our hash table for homework number 5. This is an array of linked lists. So each one of them is a linked list. This is a linked list, 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 so on and so forth. When I hash an object to a particular bucket, I add it to the linked list of that bucket. So the first person hashed into bucket number 3, it's going to be an object that is in that linked list. Nobody comes after me. I'm the last one in this list. Okay? Another object hashes to bucket number 6. Person number 2 sits over here. Person number 3 hashes to bucket number 1. He sits over here. He or she sits over there. I get person number 4, and they also hash to bucket number 3. It's very easy. I go to bucket number 3. I add person number 4 to here. So I'm dealing with overflow by having each element that overflows in that bucket sit in the same linked list as all of the other elements that hash to that same bucket. Okay, so far so good?
Yeah, I think like with this question, I'll probably be good. So I guess my original question was really about the different ways you can avoid collision. So I'm guessing it's basically it's based on the data structure you use, because if you use like an array for your list, you'd have to do the not checked yet, or is it that
Well, I'm coming to those. I just want to make sure that you understand this part.
Yeah.
So here we have collision. P1 and P4 both hash to the same bucket. But the way I'm resolving the conflict of the same hashing into the same bucket, because I am allowing multiple things to sit in the same bucket, since the bucket in this case is nothing but a linked list. So I can put multiple things into the same bucket. There's room in that bucket to put multiple things. Okay? This is okay. All right, so let's move into the one that you're talking about. Okay, there are different strategies. Okay, if I have this array, again, same array, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8. Sorry, I have to turn this off. Okay, so so this is my array, 0, 1, 2, 3, 4, 5, 6, 7, 8. Now I don't have linked lists in here. Okay, this is the strategy where I say there are different ways. This is, I think, what you're referring to. There's the linear search for finding the next bucket. So again, let's take person number 1. Person number 1 came, and person number 1 was put directly into the array. This is not an array. This is an array of person. Okay, this is an array of person type. Not a linked list, this array. This is an array of person type. Person number 2, we said hashed into number 6. So person number 2 got put there. Person number 3 got hashed into bucket number 1. Okay? Now person number 4 comes and they want to hash into the same place in here in bucket number 3, but bucket number 3 is empty, is already occupied. So there are different strategies for dealing with this, and I think that's what you're talking about, Henry, is if I go to put person number 4 in here, there's no room for him in bucket number 3. So there are different ways of finding the next bucket that I look for, okay? And one of the ways is a linear search. In other words, I go to the next bucket. Bucket number 3 was full. Let me look at bucket number 4. Well, bucket number 4 is not full, so I'm going to put person number 4 in here. Okay? And then I get person number 5. Okay? In this scenario here, person number 5 hashes into bucket number 5. Okay? Person number 5 hashes into bucket number 5. So I put person number 5 if I have this kind of hash table. If I have this kind of hash table, person number 5 will sit in here. Okay? Now I get person number 6. Person number 6 hashes to bucket number 3. In this format, I would just add person number 6 over here. Correct? If I go to this table over here, it hashes to table number 3. So there's no room in bucket number 3. I go to look at 4. There's no room in 4 either. I go look at 5. There's nothing in 5. There's no room in 5. I go look at 6. There's no room in 6. I go to look in bucket number 7. Oh, look at that. I can put person number 6 there. Okay? So far, so good. That's the linear way of finding the next one.
Yeah.
There's also the quadratic way, which your book will discuss. I'm not going to get into it right now. There's a formula that they use to calculate the next bucket.
All
Okay?
right. So all right. So I guess I finally remember the term. It's like probing, right? This is
Probing.
like what you have to do. All right. Do you have to probe when you use linked list too? Like,
No.
like would it ever like come in a situation? No, right?
No.
Yeah. All right.
Linked list has no probing.
All right.
Each bucket handles overflow. I can have multiple things in a bucket. That's the advantage of this one. Okay? Each bucket can hold multiple things. So I don't need to probe because you're never going to get to the point where you're going to say, oh, this list is full. I can keep adding to a linked list. Okay?
Yeah. All right. I think I understand now.
In this format here, I got a probe. And empty since the beginning is because of the following. Now remember in here, there are 3 things that hash to bucket number 3. Okay? There are 3 things that hash to bucket number 3. P1, P4, and P6. P1, P4, I'm sorry, I wanted to make that a different color. P1, why is that not taking? P1, P4, and P6, all hash to bucket number 3, really. So now I go looking for P1, right? I go look for P1, I hash it, it comes out to bucket number 3, I go, I find it, I take it out, right? I look at it, do whatever I want to do with it. If I'm looking for P4, I'm gonna come to bucket number 3 because it hashed to bucket number 3, and I'm gonna say, oh, the element that's there does not have the key of P4. So I probe the next bucket. The probing would be going to bucket number 4, and I look at it and say, yep, you have the key of P4. So I found it. If I'm looking for P6, I would have to probe P3. No, I would probe bucket number 4. Then I would probe bucket number 5. Then I would probe bucket number 6. Then I would probe bucket number 7 and find it. Notice all the buckets that I probed had something in them. Okay? But what happens if, since I put P6 in there, somebody came in here and said, delete P5? Well, if I'm deleting P5 in this format, okay, in this kind of table, I just remove P5 from here and we're done, right? But in this format, I just remove P5 from in here. And now I'm looking for P6. Okay? I look at probe bucket number 3, not there. I probe bucket number 4, not there. I look at bucket number 5, I say, oh, bucket number 5 is empty. So P6 must not be here. P6 must not be in this hash table, because if it was, there's an empty spot that it would have been here. Okay? The problem is that this bucket is empty, and if this bucket number 5 is empty, then it's telling me that I haven't found it by probing, so it's not there. Unless, okay, there is a flag associated with this that says empty from beginning. This bucket here is empty from the beginning. This bucket over here is empty from the beginning. And this bucket over here is empty from the beginning. But bucket number 5 is not empty from the beginning. It had something in it, and that something was removed. When I go to probe for P6, I examine bucket number 3. It's full, but it's not what I want. I probe the next one, bucket number 4. I check the key, it's not the same. I go to bucket number 5, I say it's empty, but it's not empty from the beginning, so there might have been something in there when I went to insert the P6 that I'm looking for. So I'll keep searching, probing beyond this empty bucket. Normally, if you hit an empty bucket that's been empty from the beginning in probing, it means the element you're looking for is not in the hash table. But if you hit a blank cell, blank bucket, that was not empty from the beginning, that means I keep probing to look for the thing that I want to look for. Does that answer your question, Henry?
Yeah. Now I see the difference between like the searching and actually inserting the items.
Okay, that's it. That's all there is to it.
All right, thank you.
Sure. Anybody else?
Professor, could we go over the concept of breadth first search and
Breadth first search.
Yeah, and the other first search as well.
Depth first search. There's breadth first search and depth first search.
Yeah.
Right? Okay, so the breadth first search is actually the easier one here. Okay? But you start in a graph from the vertex that you're going to start from. Okay? Okay, I'm going to start from vertex A. I have B, C, D, E, F, G, and H. Okay? But breadth first search says, I'm going to start at vertex A. I'm going to start here. I'm going to number all the vertices. Okay? I'm going to give them a distance of 0. They all start out with a distance of 0. Okay? And I start at the first vertex that I'm going to. Okay? The first vertex that I'm starting from, it has a distance 0 of itself. It says all the vertices, okay? And let's say this is a directed graph. Let's make it a directed graph, all right? All of the vertices that I can reach directly from A, okay? I am going to go and give each one of these edges has a distance, right? 3, 4, 7, 8, 2, 1, 4, 5, 3. Okay? So to get from A to B, it's a distance of 3. To get from A to C, it's a distance of 4. To get from A to D is a distance of 7. So when I'm at A, I'm going to take all the vertices that I can reach directly from A, and I'm going to give them their distance. That's how far you are from A. So B will get the distance from A is 3. This one has a distance of 4, and this one has a distance of 3. Okay? And then I go to the next one. Now, I have A, B, and C that I have put into a queue. B,
Professor.
C, and D. Yes?
Is that supposed to be 3 or 7? I don't know.
From
For
A
me,
to D.
No,
is-
7.
Okay.
Never mind. Okay, these are the vertices that I found from A. I put them into the queue and I go back over them each one at a time. Okay, who are all the ones that I can reach from D, from B? Okay, because he was the first one in the queue. I take him off the queue. I say, B, where can you go? You can go to F. Well, whatever is the distance to B plus 1 is the distance to F. Okay, which is 4 now. Okay, that's what his distance is. And I go to C and take him off the queue. And when I'm looking at F, I say, who can you reach from F? And F says, oh, well, I can reach from F, I can reach H, right? I add him to the queue. And now I take C. I say, who can you reach from C? He says, oh, I can reach E. And well, C to E is a distance of 2. 4 plus 2 makes E a distance of 6. Okay? And then I then remove D. I say, who can you reach from D? He says, I can reach G. I put G in here. And I say the distance to D, to G is 7 plus 8. So this is 15. Okay? And now I go to F. I go to H. H is the next one here that I have, right? No, I have F in here. And F is ahead of H. So I go to F and I say, F, what can you get to? Well, I can get to H. Well, H is in the list already. There's no big deal. And I ask, how long is the distance from F to H? And that becomes 8, right? And when I go to look, H is at the bottom over here. E says 6 plus 5 is 11. Well, 11 is bigger than 8. So the distance to H is 8, really. It's still, the best distance is 8. And when I go to look at G, G tells me 15 plus 3 is 18. That's still bigger than 8. So H is reachable in 8 steps. Okay, and when I go to H, there's nothing there that I can reach that has not been reached already. And as I'm going through, I'm marking the vertices as having been visited. And I keep looking for unvisited vertices to keep finding and adding to the queue. Okay. And then when I'm finished with when the queue is empty, I have calculated the minimum distance to all the vertices that I have in my queue. Okay. That's breadth first search. I want to find everything I can reach directly, and then I go to the next level. Okay. A can reach B, C, and D. Well, okay, now go to B. Who can B reach? Who can C reach? Who can D reach? And then I keep stepping through the graph that way, expanding my understanding of the graph as I go. Depth first search, okay, says I am looking in this case at A to B. Okay, well, all right, I found B. Who can B reach? B can reach F. Okay, very good. B can reach F, and F can reach H. Okay, very good. Then I calculate the distance to H, being 3 plus 1 plus 4 is 8. And then I come back. I say, oh, A can also reach C. So where can I go from C? And I explore everything directly from C. And then I go back to D and explore D. In breadth first search, we start out by looking at all the vertices that are adjacent to me. I deal with all of them, and then I take one step further. In depth first search, I find all the vertices that I want to reach. I pick one of them, and I do the same thing. I keep following that as far as I can go from that one before coming back and taking a look at the next vertex that I want to look at. Okay, so in this case, A would look at B, B will find F and then H, and then I'll go back and look at C to find E and then H, and then I'll go back and look at D to find G and then H. So depth first search means go as far as you can in this direction and then come back and pick the next vertex and go. Okay?
So would you, when you say go back, would you go back to A, or would you just go back to one of the vertices that were adjacent
when you were at A, you took the vertices A, B, you took the vertices B, C, and D, and you push them onto a stack, and then you pop them off one at a time.
Oh, so the ones that go on the stack B, C, and D are the ones that you go back to?
So
Okay.
you have a stack, okay? And let's say I push them in the following order, D, C, and B. Okay, B is the top of the stack. I pop B. I say, okay, I'm there, I got B. And now what does B reach? Well, I'll push F. Okay, I'll pop F and say, who can F reach? I'll say H. I'll pop H and look, and H cannot reach anybody. So then I'll go back and pop C off. And now I follow C. C says I can reach E. Well, E then gets popped off, and then H gets put on here, and then H gets taken off again. And then I'll pop D, and D says I can reach G. So it's take one, everything that one can reach, push it onto the stack, and now go and pop things off the stack and deal with it that way. Okay? Look at the detailed algorithm is written in your book. We followed it in class. We did it in class. So go ahead and play with that. Anybody else? Does that answer your question, Johnny?
Yeah. And I guess, did you go over depth? Or, because this is breadth.
This is depth first search that I'm just talking about now.
This is depth with the D?
I did breadth first, and then I talked about depth.
Okay.
Okay? Anybody else? Anybody have any questions about their progress reports? Okay, good. I'm going to put out the new progress reports after class when we finish. So if you do have an A- or an A in the course at this point, you are exempt from having to take the final. But if you take the final, it will count. That's up to you. Okay? Questions?
So if I have A minus, and I take the final exam and I get good grades, so I can get A.
You could if you want, yeah, if you wanted to. So you
Okay,
could get a good grade and bump your grade up to an A, or you could get a bad grade and bump your grade down to a B or a B plus.
If I'm not doing good on the final exam.
Right. Because the final exam counts.
Understandable. Okay. Okay. But
So
it's kind of tricky
raise
then.
your grade, you could lower your grade. It depends on how well you do on the final.
And if I have the A minus and don't take the final grade is gonna be A minus.
Whatever is on your progress report right now, if you are exempt, whatever is on your progress report is the grade that will go in for your course, for the course.
Makes sense. Okay. Thank you, Professor.
Sure, Caitlin.
Okay.
Good question. Anybody else?
I just have like a follow-up with that. So like, would you like just tell us that we're exempt, or just based on our progress report, we could just assume we're exempt based on the grade?
If the grade says it's an
Okay.
A or an A minus, then you are by definition exempt if you are present here today.
Oh, okay.
People
thank
who have an A or an A minus but are not present when I take attendance today are not exempt from having to take the final.
Professor, and another thing, you said you were gonna post the progress report on Slack, but I didn't see it.
Did you look on Slack and you didn't see your progress report?
Yeah, I was looking at it and I'm gonna double check, but I didn't see it. I'm gonna check one more time.
It's a private message from me to you.
Okay, let me look. Yeah, after the class, I'm gonna look
Well,
at
look now. I mean, it's there. I can see it. I'm looking at it.
it. Okay. Let me.
That's the progress report I sent on Thursday.
Okay, hold on.
This is not the new one. I'm sending a new one.
No, I know
after
you're
today.
sending a new one. Okay, perfect. Let me
Okay.
check.
There are some people in the class who did not join Slack, which I don't understand why you wouldn't join Slack. And I emailed you those progress reports. Okay, I emailed them to your Lehman email address. Any other questions? Zahra, did you answer your question about the progress reports?
Yeah, thank you.
Sure. Caitlin, you okay?
Yeah, I'm looking at it. Professor.
Okay. Anybody else? Okay, let's take attendance. And then we'll see if there are any more questions. So let's start at the very beginning. We're going to go one at a time. Kelvin Abraham, present. Hold on one second. Yep, Kelvin is present. Sayed Ahmed, absent. Chris Kevin Andrade, present. Eric Aragundi, present. Grecia Carolina Ardiles. Grecia, are you here? No, absent. Madeline Ayala, present, thank you. Alexia Blake, present, thank you. Jessica Campos, thank you. Jonathan Campos, thank you. Natalie Falcon, thank you. Tyrese Ford is absent. Cruz Gonzalez, thank you. Travis Headley, thank you. Victor Ibitoye absent. Alauri Jorge, absent. Radwan Khan, absent. Zahra Khan, present. Ali Kuruma, present. Sandra Leon, absent. Stanley Nunez Martinez, present. Stephen Otun, present. Henry Ovalle, present. Cesar Peña, absent. Leslie Quesada, present. Dejan Rudolph, present. Caitlin Santos, present. Ajani Scott, present. Giassi Sturgis Finney, absent. And Luis Vasquez Gonzalez, present. Okay. Just let me take a look over here. All right. Anybody else?
Quick question. What's the like relationship between like a graph and a tree? Or like, would you say like all graphs are trees, or like, is it the other way around?
Okay, it's the other way around. All trees are graphs, but all graphs are not trees. That's actually a good question. Let's take a look at it together. So let's make a tree, and let's show you the difference between a tree and a graph. A tree is essentially a graph that has no cycles. Okay? A tree is essentially a graph that has no cycles. Okay, there's no cycles. I cannot start walking somewhere in the tree. By a cycle, I mean, I visited this node, I visited this node, I visited this node. There's nowhere else I can go to bring me back to a node that I have already visited. Okay? Without having to go and touch nodes that I have not visited before. A graph is like this, but I can have this in a graph. This is a graph. I can start here. I can go there, go there, go there, and then I can come back to the node that I started from. Okay, it brings me back to the node I started from. So I can navigate this graph by going in this cycle. I can navigate this graph by going in this cycle too. Okay, so graphs can have cycles, but trees never have a cycle in them. Okay, trees don't have any cycles in them. Graphs can have cycles. All right, that's one of the differences between trees and graphs.
All right, thank you.
Mm-hmm. Graphs can be directed. Trees are not generally, I mean, they are directional in the sense that child-parent relationship is directional. The other difference in a graph is graph edges can have weights, 5, 4, 3. Tree edges don't tend to have weights. Okay? So those are some of the differences between trees and graphs. But
Would you
other than
say-
that, a tree is a subset of a graph.
Would you say like in general, like the ways that like trees can have weights are like just a height and just like assuming like all edges are just one?
All edges are of the distance 1 in a tree.
All right.
There's no other weights than that.
Professor,
Yeah.
I'm not sure if that's part of the book, but in here we also need to know like what is a simple graph or a bipartite graph or something like that.
Say that again.
So I know there's different kind of graphs. So we don't know the different kind of graphs, right? We don't need to know that.
Well, there's different kinds of graphs, right? There's connected and disconnected graphs, right? So this graph is all connected, right? But I can have a graph that is not fully connected, right? I can have this. And then I can have another set of nodes that are interconnected over here. So this is a disconnected graph. It is one graph that is kind of like got 2 parts to it. You can't get from here to there. There's no path that takes you from one node to another node in a different part of the graph. So this is a disconnected graph, okay? This subgraph on the left-hand side is an acyclical graph. Doesn't have any cycles in it. This one has cycles in it. Okay, so there's cyclical, there's acyclical, there's connected, there's disconnected, there's directional and non-directional, bidirectional. These are all bidirectional. A directional edge would be if the edges had arrows on them. Okay, so all of these different kinds of graphs. What other kind of graphs are you talking about, Eric?
I was reading something about simple graph. There's a definition for a graph to be simple and something called bipartite, where you can split a graph into 2 and actually 2 sets of. So I read something about it, but I'm not sure if that's also included on the book and it's part.
Okay, so one of the things that you can do in a graph is you can find the minimum spanning tree of a graph. Okay, where you take the full graph and you delete the edges that are not needed, but keep all the vertices and the edges that transform the graph into a tree, the minimum tree. That gives you the minimum number of edges that contains all the vertices that are in that graph. So that is a minimum spanning tree on the graph, and there's nice algorithms for doing that in there, talked about in your book.
Oh, nice.
Okay. And then there's this whole thing about sorting the nodes into order in a graph. We talked about that. To come up with for your a topological sort of your nodes. We talked about topological sort. We didn't talk about minimum spanning trees. Okay. But we did talk about topological sort. And we gave the example of courses and their prerequisites, and you can represent them as a graph and then come up with the optimal way of what are all the possible ways you can take all your courses in what sequence in order to accomplish what you need.
Professor, and the questions in the exam, they will come from the side book, right?
They come from the Zybook and they come from my head too.
Oh, okay.
They come from both. Some of them come from the Zybook and some of them come from my head. But they are all on the topics that we have talked about.
These are like the topics from the beginning of the semester, right? Like the whole.
The final exam covers chapters 1 through 8.
Oh, okay.
The whole semester. It's comprehensive. It covers the entire semester, inclusive. Okay. Yeah, it's inclusive. Chris says, you know, Eric sounds like he'll take the exam for fun. He may be crazy, but I don't think he's that crazy.
Are there any questions going to be extra credit, or is it just going to be straight on multiple choice questions?
What do you mean by extra credit? I'm sorry.
Or like any other multiple choice going to be, I don't know, is there any like leeway, I guess, as to like the multiple choice, or is it?
The exam has more than 100 points in it, yes.
All right.
Like all of my exams, the exam has over 100 points in it. Anybody else? Well, if you don't have any questions for me, then this review is done and this course is done. I really would appreciate it. Some of you have actually filled out the survey. I would appreciate if more of you fill out the survey.
I have a question before.
Yeah, sure, Caitlin.
Yeah, I already saw the report. And what it says overall grade, that's the final grade, right?
Yes.
Okay, perfect. So I guess, okay.
Okay.
Yeah, thank you, Professor.
Thank you.
Professor,
Yes.
I do have a question of something that I'm still a little bit foggy about and might be useful for the class. Can you explain a little bit again about the traversal of a tree, like in order, post order, pre-order?
Okay. We could do that.
Because when I was working on the homework, I was trying to do set testings without tree that I created myself. But I was a little bit foggy, like if I get the numbers in pre-order, how to build the tree back from those numbers.
Okay, so let's do that. Let me share my screen again. And here's a tree. And I'm going to put some numbers in here. Okay, so this is going to be 25. That's going to be 15 and 45. And this is 10 and 20. And that's 30 and 50. Okay, so here's a tree, a binary search tree for that matter. Okay, the way that in order traversal happens, okay, the algorithm for in order traversal is in order, okay, node, okay, and in order traversal, I do in order left, visit, and in order right. And by right and left, I mean go to the left child and do in order. So if I'm doing in order on this tree over here, and I'm going to follow the stack. So I'm at 25. Okay. 25 goes in the stack. Sorry, we're going to do the stack the other way around. Okay, we're going to do it 25. I'm going to visit the left child of 25. right? Because I'm going left over here. So I'm going to visit 15. Okay. And then I'm going to visit 10. I'm going to get to 10. So I'm still doing this part over here, the in order left. If I ever go to the left of 10, the left of 10 is a null, right? Because there's nothing here, right? When it's null, I return and I visit the nodes that I'm at. So the null, I return from it and I visit the 10, which outputs 10. And 10 is the smallest value in this whole thing, which means I go back to 15 and then I visit its right child, which is 20. And 20 goes to visit his left child and there's nobody there, right? There's nobody there. So he comes back to 20 and outputs to 20 and tries to visit the right child. There's nothing there, comes back and returns to 15, okay? I mean, sorry, the 15 would have come out before the 20 has gone to. So 15 comes out and then the 20 comes out and then the 25 and then it visits the 45, 30, so on and so forth. When I look at the order in which the nodes were visited, in this case, they're going to come out in order of 10, 15, 20, 25, 30, 45, 50. That's in order. If I visit nodes in pre-order, the same tree in pre-order, okay? Let's visit this node in this tree in pre-order. Pre-order is slightly different, okay? In the sense that pre-order has this visit comes first in the algorithm. Okay, so I'm going to visit these nodes in pre-order. I'm going to output the nodes as I get to them. Okay, so I am at 25, it puts out 25. Okay, and then it goes to the left child. The left child is 15. When I get to 15, it puts out 15. And then I visit the left child of 15, which is 10. It outputs 10. Okay? And then I go to the left child of 10, and that's null. There's nothing there. I go back to 10. I visit the right child. Nothing there. Fine. Go back to 10. We're done. Go back to 15. All right? I go back to 15. I visit his right child, and that's 20. Okay? I visit the left child of 20, nothing there. Right child of 20, nothing there. I go back to 15, I'm done. I go back to 25. I go to his right child and it's 45. So 45. And then I visit his left child. So it outputs 30 first, right? And then I go visit left child, right child of 30, nothing there. I go back to 45. I come back and I output 50. When I look at the nodes in pre-order, the first node is going to be the root. That's always the root. The first node is the root. Okay? The next node after that is going to be its left child, if there is a left child. If it's smaller than 25, it's going to be the left child of 25. If the next node is smaller than it, then it's also the left child of 15. Okay, so I can start building this tree by going through this order. 25, 15 is a left child, 10 is a left child of 15, and then I look at 20, I say, oh, 20, well, 20 must be the right child of 15 because it's bigger than 15, okay? It couldn't be the right child of 10. There's no way it could be the right child of 10. Because 20 is bigger than 15, so it can't be to the left of 15. So 20 will have to be here. And then when I get to 45, I know that I've gone to the right-hand side of the root, so this must be the right-hand child, and this must be the left child, and this must be the right child, and now I can rebuild the tree from the pre-order traversal. Pre-order traversal is the one that you can use to build the tree from.
Quick question. When you got to the 20, why did you say that it cannot be the right child of 20?
Why can't it be the right child of 10?
No. When you got to the 20, why the 45 cannot be the right child of 20?
Sorry, say that again. So 20, I said 20 can't be the right child of 10.
No, I mean 45. Why 45 cannot be the right child of 20?
It cannot be because it's bigger than 25. Right? The root is 25. 45 cannot be to his left. Right? If I put 20 over here, right? If I put 20 over here, right? 20 is here. And you're saying, why can't 45 be here? Well, because 45 that way is in the left subtree of 25, and that is not a binary search tree. Because 45 is bigger than 25, so he cannot be in his left subtree. Does that make sense, Eric? Thinking. Anybody else have a question about that? Because 45 cannot be in the left subtree of 25. He has to be in the right subtree of 25. That's how I know to put him there. And since he comes right after 20, it must be that he is the immediate right child of the root. Okay? And post-order traversal is exactly the opposite of all of those. Post-order traversal does the traversal as we do it. This is pre-order. And that's now we're going to do post-order, which means the visit comes at the very end. Okay? In which case, I visit everything to the left and everything to the right before I can output myself. Okay? So what does that do? I visit 25. I visit 25. I go to 25, which then takes me to 15, which then takes me to 10, which then takes me to his left child, right child, and then 10 comes out. Okay, I visited both children of 10, so now 10 can come up. Then I go back to 15, then I go back to 15, okay, and I visit his right child, which is 20, and then I visit the left child and the right child of 20, and now 20 can come up, okay? And now that I go back to 15, I have dealt with both his left child and his right child, so now 15 comes out, okay? That's post order. Now I get back to 25, I have dealt with all of his left subtree, but I haven't dealt with his right subtree yet. So I go to 45, and 45 leads me to 30, and 30 visits left, right, and then 30 can come out. And then I go back to 45, and I haven't finished his right subtree. I go to 50, visit his left child, right child, then 50 comes out. And now when I go back to 45, 45 can come out, and now 25 will come out last. So the root in a post order is always the last node in the post order. In a pre-order, the root always comes first. You can build the tree out of a post order also. Okay, the in-order traversal is the only one that doesn't give you a hint as to what the structure of the tree is. Okay, other questions?
Professor,
Yeah.
I think you saw my message on Slack, and I think you mentioned earlier that you were fixing the errors with like the participation activities and stuff. When will you be resending the revised reports?
As soon as this class is over.
Okay, and then based on that and the fact that like the people who were here today, like whether you have an A or A minus, like just to like clarify, like it's not mandatory to take the final.
You can't believe whether that you are exempt from the final? Is that what you're saying?
Yeah, and I just want to make sure before like.
Okay, let me speak to you directly, Natalie. You are
Okay.
exempt from having to take the final.
Okay. Thank you.
You're welcome. I know it's hard to
I
believe.
think
sometimes.
everybody had that. Everyone that here is like exempt from final just doesn't believe it.
Yeah, I was like, what?
The same.
Yep, no, you are exempt from the final.
Okay, thank you, Professor.
Sure. Anybody else wants to hear directly from me?
Yeah, what about me, Professor? Yeah, because it's like kind of unbelievable, you know?
Yeah, Caitlin,
Yeah, boss.
you are exempt from the final.
Okay, thank you. Okay, thank you, Professor. Okay.
Anybody else wants to know, hear from me directly?
I kind of want to know.
Who's that? Who's speaking right now?
Zara.
Zahra? Zahra, you are exempt from the final as well.
Okay, thank you.
What about me, Professor Luis?
I haven't gotten to you yet because I'm still doing the progress reports. Okay, but look on, sorry, Luis, I haven't gotten to yours yet. Okay. But my sense is by looking at your grade is you're awfully close. So I'm gonna have to take a look to update your grade based on what you have done in chapter 6, chapter 8 and homework 6. Okay, based on that, it's gonna decide. Look, I'm gonna put it out on Slack in a little bit, so you'll be able to see it.
All right, thank you, Professor.
Anybody else?
Sorry for that. A quick question. So this is not for example. I know everybody's asking. This is more towards just the order that we just went to. So every time you hit the instruction or get to the instruction visit, that's when it returns the node that you're currently at.
That's when you output, put it into that list, because each one of those is generating a list for you, right?
Oh, okay.
And visit means put it in the list.
Okay.
Okay, do whatever it is that you're doing with it, but in our case, it's just put it into the list. Okay.
Okay.
Anybody else?
What?
Wait, could everybody mute themselves so that we're not fighting over each other with sound? Johnny, go ahead.
So in terms of, I guess, like methods like these when you're doing recursive, and let's say for instance, like I know there are times where you might get a recursive method, and well, you might turn a non-recursive method like you do a binary search into a recursive method, and there are times where you might not. You might just get the recursive method, and I guess just have to follow through the algorithm with that. Basically, my question is like, what advice would you give in terms of like, I guess, breaking down a recursive method? Because sometimes it can be a lot hard to follow through in a sense, like even going line by line.
So recursive methods obviously have a terminating condition. That's very important, that you see that your method has a clear base case, which we call a base case. That's the terminating condition. Okay. So that's an important thing to have in a recursive method. Okay. Aside from that, okay, you need to make sure that your recursive method is, you follow it the way I follow it with these stacks that I draw. Okay, because remember, every time you call the method, it creates the next stack frame that gets pushed onto the stack. Okay, and I'm drawing these stack frames upside down, but really stacks go from bottom up. But for some reason, computer scientists always draw stacks from top to bottom. But they really are more like a bottom to top because you push onto the stack. Okay, so yes, you have to make sure that you're handling the base case is the most important part, because otherwise your stack is going to go, I mean, your recursive algorithm is going to run into infinity, which is going to be, you're going to end up with being out of memory, stack overflow, which is some of you have run into with the homework. Okay. If you don't have your terminating condition done properly, then you're going to end up with a problem there. Okay. Recursive methods. Okay, here's the thing about recursive programming. I got to tell you that in all of my years of writing code for projects that I have worked on, the number of times that I've actually written code that was recursive, I could probably count it on the fingers of one hand. That's very few. And I've been programming for a really long time. So you're not going to generally write recursive code. Recursive code is very useful and very handy, and is a really cool trick to get around having to write iterative code. The code ends up being a lot simpler when you write it in recursive mode, especially for data structures like trees and graphs. Okay, those two types of data structures kind of like beg for recursion. Aside from that, I have never had the occasion of needing to write a recursive code out of the clear blue sky. Okay, I've written recursive code for trees, I've written recursive code for graphs, I've written but those are all well-known algorithms that you can just look them up in a book and write them. I have never written a recursive algorithm from scratch when I was programming in the real world. Okay. Does that mean that you're not going to get asked recursive questions when you go for an interview? You are. They're going to ask you recursive questions. I don't know why they ask these kind of esoteric kind of questions in interviews, because they tend to not be real life problems that you run into on a regular basis. But if you see a recursive program, a recursive function, you should be able to trace it. You should be able to walk through it, create a data structure that kind of like you want to walk through with that recursive algorithm, and then walk through it. If it's a tree, make a graph or tree and then walk through it. And if it's a graph, make a graph and then walk through it and see if it's doing what you expect it to do. All right. I don't have any other advice as far as recursion, other than just making sure there is a base case, and that, you know, it's always gonna terminate at some point.
Professor.
Yeah.
I want to point out something. I hope in the future, maybe for this CMP course or any other CMP course, you professor can include maybe a class about debugging, because it's very useful. Like when you use the debug mode, you can say clearly where you are stuck and what part is getting the infinite loop.
Yeah, you mean like to learn how to use the debugger in Eclipse?
Yes, because I have taken like already like 4 CMP classes, and none of them teach how to use the debugger.
That's a very good point, Eric. Thank you very much for that. Did you put that into your comments on the evaluation of the course?
Actually, I forgot. I forgot to put it.
Okay, so that's an excellent comment. I will definitely. I think what we need, there's a few things that we don't cover in our courses that are very important. You know, one of them is GitHub.
Yeah, that's also.
Okay, that's something that is really useful, but we've held workshops on GitHub that are outside the courses. And I do think that we should hold a workshop on debugging also.
Yeah, those are very useful too. Maybe also like include some like shortcuts, because there are like shortcuts in programming that are very useful too.
Mm-hmm. Like what, for example?
Like when you do sys out and you press control space, that you have mentioned some in here, but there are like very useful tricks, like the correct indentation that you just go and the program do it for yourself. Some students don't know about it.
Right.
So there's like some useful stuff that I think that it will be good to cover either in class or do a workshop about it.
So I think a workshop around programming 2 time might be a good place to introduce, like when you're taking 168, to
Yeah.
have a separate workshop on debugging.
Yeah, that's
and
very good.
tricks. Debugging is 90% of your time as a programmer is going to be spent debugging.
Yeah.
You know,
I think you do a survey for the students to know how many of them know about the debugger, and you're gonna encounter at least 80% of the students do not know about the
Right.
debugger.
That's true. That's true. What was it? I just saw a thing that was very funny. It said the only web developer that enjoys finding bugs are spiders.
Yeah. That was the picture you sent you, right?
Right. Oh, you were the one who sent that to me.
Yeah,
Okay.
I sent it to you.
I just saw that recently. You sent it to me like a couple of weeks ago. And I've been quoting that over and over again. So yeah, no, debugging is a huge part of your life as a programmer. Okay. And it is really frustrating unless you develop the right set of tools in order to debug with. And I'm going to take this comment and I'm going to pass it on to people who teach 168 to have a workshop to do debugging, to teach debugger, to use how to use the debugger.
Thank you, Professor.
Because setting breakpoints and all those kind of things and tracing variables and all of that is really useful. Really useful.
Yeah.
Anybody else? Thank you for that. Okay. So was there anybody who was not present when I took attendance and are present right now? There was a few people who were missing when I took attendance. Let me just go back and double check whether they're here now. I'm going to call your name one more time. Sayyid Ahmed, are you present? No. Grecia Carolina Ardiles? No. Tyrese Ford? No. Victor Ibitoye? No. Alauri Jorge? Radwan Khan? Sandra Leon? And Cesar Peña? And Giassi Finney. Okay, these people are absent. Okay. All right, folks, you guys have been a really wonderful class. I have really enjoyed having you in my class. I know I have been hard in my homework that I've given you. I've given you a lot of things to do, but I hope you have learned a lot in this course and are ready to move forward with your education in computer science. Thank you very much for being in my class.
Thank you, Professor,
you,
for teaching us.
All right, all right. So
Professor,
yes,
before you go, just one last question.
yes.
I promise, the last one.
No, there's no last questions. There's always more questions.
For this class, at least. You said you gotta check again my report, right?
Mhm.
So are you gonna send it again, like
Yes, yes.
updated?
I'm gonna put everybody's reports back out on Slack.
Oh yeah. Okay, no problem.
I was working on it before class today, and I didn't get to finish them.
I just wanted to make sure. So in order to be exempt from the test, you gotta get an A.
A or A minus.
Okay, no problem.
Okay.
Thank you, Professor.
In other words, an average of 90 or above.
Okay, sounds good. Thank you for
Okay.
everything, Professor. It was a good semester.
It was a great semester. I enjoyed having all of you in my class.
Thank you, Professor. If I have any question in the future, I can email you.
You can email me. You can come to my office hours.
Okay.
Eventually, hopefully by next semester or the semester afterwards, we're going to be present in person. So you'll actually be able to come to my office.
Right, and I think I'm gonna take another class with you. So, okay, perfect.
I
Thank you.
hope I see you all in my classes in the future.
Thank you, Professor.
All right.
All right, have a good one.
You too. Bye.
Bye.
Thank you, Professor.
Thank you. Thank you, Zahra. Take care.